Hello, dear colleagues. In this discussion, we're going to be looking at chemical kinetics, and basically, we are going to be introducing this area and talking about concepts and applications. To begin with, we need to define what chemical kinetics is. So, we know this is the branch of chemistry that deals with the measurement of reaction velocities or speeds, stroke rates, and determination of mechanisms by which reactants are converted into products. We find that when we have reactants giving products, in most cases, the way we present our chemical reactions is actually not how that reaction is taking place, but sometimes it goes through a series of reactions whereby you have some intermediate products, and those intermediate products react again to give the final products. Now, the knowledge of chemical kinetics is useful in altering the rates of chemical reaction when needed. So, for instance, in the manufacturing of fertilizers, aiming at speeding up the formation of ammonia from nitrogen and hydrogen. Yes, we could be interested in manufacturing of fertilizers, and then we want to look at how do we form ammonia very fast from nitrogen and hydrogen. Whereas a car manufacturer could be interested in slowing down the rate at which iron does rust. Yes, because in car manufacturing, we are producing a product, for example, a chassis that is going to last longer for a number of years. So, if we find that this is iron that is being used, we need to carry out a number of investigations to see what is causing rusting, because rusting itself is a chemical reaction. So, in order to look at the products of this reaction, of course, we write maybe the equation, but then we also need to understand the effects of rusting. So if we find that the effects of rusting are very negative or are very really bad and unwanted in any industry that is dealing with steel and iron, then we need to study a reaction that is aiming at slowing down iron. That is why, in most cases, you hear about electroporating, you hear about to now do manufacturing or applying a particular paint that is going to slow down the rate of reaction that involves rust formation. Because rust itself affects the strength and degrades the iron materials over time. So let's look at the practical applications of chemical kinetics in the real world. As we have earlier on said, we have chemical kinetics used or applied at an industrial level. So industrial reaction optimization is one practical application of chemical kinetics, where we are looking at optimizing the reaction conditions in industries like pharmaceuticals, petrochemicals, and polymer production. An example could be the production of ammonia synthesis in the Haber process. So, what is the Haber process? The Haber process involves the reaction in which hydrogen and nitrogen react to produce ammonia. So, we are going to have the equation. So, we have nitrogen as a gas reacting with hydrogen, which is a gas, to produce ammonia gas. So we can do the balancing. We put our 2 here, and we can put a 3 here. Then another example, we find that chemical kinetics helps us to determine the optimal temperature, pressure, and use of catalysts to maximize yield while minimizing costs. So in the production of, for example, ammonia in herbal process, the chemical kinetics will help us to determine the optimal temperature, application of pressure or which pressure do we need, and then the use of catalysts to maximize yield of, for example, ammonia, and while we are minimizing the costs of production. Another practical application is in environmental science, where understanding and the mitigation of pollution is very important. And under that, we shall be looking at studying the decomposition rates of pollutants like ozone in the atmosphere. We know ozone is important at a particular level of atmosphere, that is the stratosphere, and then the troposphere. That's where we have this ozone near the Earth's surface, and this becomes a very dangerous gas. But at the stratospheric level, we find that ozone is very important because it reacts. Okay, it forms a layer that absorbs ultraviolet light rays that actually protects us from skin cancer and other issues like cataracts. Then, so in understanding the decomposition of this ozone, for example, when we are minimizing it at troposphere level, then chemical kinetics play a very important part. Then designing the catalytic converters in vehicles to reduce harmful emissions by accelerating reactions. Of course, one of the reactions that take place there is that when you produce carbon, of course, you have carbon that is burning to produce carbon dioxide. So in case there is insufficient or incomplete combustion of carbon dioxide that produces carbon monoxide, okay, we always pass it through the catalytic chamber or catalytic converter to convert this carbon monoxide produced to carbon dioxide that may pose less harmful effects to the environment and the people around. Because carbon monoxide itself is too dangerous, once a person inhales it, it may lead even to suffocation. Because remember, this carbon monoxide has a high affinity of oxygen in the hemoglobin. So the hemoglobin carrying oxygen will release its oxygen to, of course, to okay, it will have this hemoglobin usually reacts with this carbon monoxide to form carboxy hemoglobin, which limits its ability to carry the oxygen in the blood. And once you don't have oxygen in the blood, then you are going to have suffocation. So the reaction that usually happens when we are in the catalytic converter is carbon monoxide that is oxidized again to form carbon dioxide gas. So you can do the balancing by putting a 2 here and putting a 2 here. Then the other one is monitoring the degradation of plastics and hazardous wastes is also another important practical application of chemical kinetics under saving the environment. Then the other area is the pharmacokinetics. And pharmacokinetics, we are looking at an example of drug formulation and delivery in medicine. When we are talking about design of formulas for drugs, so an example is determining the half-life of drugs in human body to design the effective dosage regimens. Then understanding how quickly drugs like aspirin break down or are absorbed in the bloodstream also helps us to understand. Once we understand this, we are able to design a better drug like aspirin, or we find a way of enhancing it so that we have a faster breakdown or a faster absorption into the bloodstream. Then the other area of application of chemical kinetics is food preservation. This involves extending the shelf life of food products. And an example of this is actually looking at application of chemical kinetics. So we use chemical kinetics to study the kinetics of food spoilage, such as the oxidation of fats or the degradation of vitamins. All these are biochemical reactions that require understanding how faster or how slow these reactions could be, and then we know what impact they have in as far as food spoilage is, or in as far as food preservation is. We also have antioxidants slow down the reaction rate of lipid oxygen. A rate of lipid oxidation. A lipid molecule like RH lipid can react with oxygen to form peroxides in a process commonly known as lipid peroxidation. So in such a chemical reaction, we have RH lipid. Okay, this is a lipid molecule. Okay, that is undergoing oxidation to form a peroxide. So this is very important because chemical kinetics will tell us how slow or faster this reaction is going to be. Of course, being governed by a number of factors. So these applications show how chemical kinetics is integral to innovation and problem solving in science and industry. So ladies and gentlemen, we are going to be entering into another discussion where we're talking about the rates of reaction. See you in the next discussion.